Welcome to RISE Learning Machines seminars. RISE is Sweden's research institute with 3,000 people working on topics spanning from bioeconomy to digital systems. Specifically, the computer science department works on applied AI projects for the benefit of society, and we organize the weekly Learning Machines seminars as part of our Center for Applied AI Research. This meeting will be recorded, and if anyone wants to be removed from this recording, please let us know. Also, make sure to check out the collection of great talks on our YouTube channel. Today, I have the pleasure to introduce Hedvig Källström, who is professor at KTH. She is also a principal AI scientist at Silo AI and an affiliated researcher in the Max Planck Institute for Intelligent Systems. She received her PhD in computer science in 2001 from KTH, and she works on topics such as interpreting human and animal behavior and cognition, and intelligence amplification. The topic today is compositional, structured, and interpretable models. With this, I will hand over the floor to you, Hedvig.
Thank you so much. It's great to be here. Let's see if I can share my screen. Like that. Do you see my screen and not the presenter view? Yes. So.
Yes.
Yeah, thanks for the introduction. Today I would like to talk about how you can learn machine learning models that are inspired by how the human brain works in different ways. So in the following, let us think of a learning system in a representation learning way. I like representation learning a lot. So then you have some input, some observations of the world. It could be images, text, or signals, other type of signals that the system receives. And then you have some kind of latent representation on which the reasoning or cognition happens. And then the output from the system, it depends, of course, on the task, on the tasks that the system have. But it's basically the outcome of this reasoning. So it could be classifications or detections or predictions of something. And such a representation is good because the system can be good at many potential downstream tasks, like imagining autonomous car that needs to be good at both at navigating to a certain goal, but also to avoid crashing into other cars and pedestrians. So basically, many specialized deep learning systems sort of cram for the exam, or they basically become specialists at a very narrow task. For example, classifying a predefined set of visual classes. So there is a lot of interesting written about representation learning, but I would recommend Benjo et al. And Sian et al. Also about why it's good with representation learning. So in the very interesting work from the group of Joshua Tenenbaum at MIT, it's pointed out that we humans are able to, and forced by nature, to learn from very sparse data. So a state-of-the-art machine learning algorithm usually learns in the following way. So you have a quite large body of training data. For example, if you want to recognize elephants, you might give the system loads of images of elephants, and it's able to identify new elephants with really high accuracy and precision. But it has been shown that toddlers, I mean very young children, like 2 years of age, who have never seen an elephant, but they've seen a lot of other animals. So they might have seen a dog and a horse, for example. And then you can say that, show a pen drawing of an elephant and say that this is an elephant. It's like a very large dog or a very large horse, but it has a long nose and big ears. And it looks like it. And then the toddler being shown the image of an elephant can say that, oh, but that's an elephant. So apparently something really different is going on here in this toddler's brain than what is going on in a deep learning framework. And this has also been confirmed by other researchers. For example, Alison Gopnik at Berkeley has done a lot of studies on how children learn things. The reason, so one of the reasons why humans learn from very few examples in this kind of reasoning way might be that we have an embodiment. So already Immanuel Kant started thinking about how our embodiment shapes the way we perceive the world. So both our perception and our cognition, how we reason about what we see, is governed by the fact that we have a body and are situated in the world. Today I'm going to talk about human-like strategies for perception and cognition, but in another line of work, I'm also interested in human behavior and communication, how humans understand each other and how a machine can infer things about a human by observing and interacting with a human. For example, a robot can learn how to perform a task by observing a human performing the same task. Or a machine might observe a human and extract sort of digital biomarkers about human behavior that can be used to diagnose certain, for example, cognitive decline or depression. So I'm interested in embodiment for many different reasons. So I'm not going to talk more about embodiment today, but if you're interested in embodiment, you might go to my homepage or contact me. This also applies to non-human animals. So you were visited 6 weeks ago by Sofia Bromé, who was my now graduated PhD student who worked with video of horses. So I'm also interested in how animals communicate their experience via their embodiment. And so see my homepage for more information about this. And what I claim, so my claim in this talk is that computers should learn more like humans. It's really good to try to make our algorithms more similar to humans. So this is argued by firstly by Alan Turing already in the 50s. So this famous paper where he talks about the Turing machine or the Turing test. But there is actually a better part of the paper, which is section 7, where he talks about that it's a better strategy to design an algorithm that learns like a child. So you should basically, the algorithm should be very simple from the beginning and then learn from training data like a child. I think this is very forward-looking from the 50s to say this. And this is also along the same lines, you also have this work by Tenenbaum et al. And Gottmik et al. But I mean, a very simple reason is that humans are the working solution out there. So it's good to look at human strategies and see why are humans so robust and efficient with data. So, but another reason is, so I think we should have a look at the UN sustainability goals. I think it's, for many reasons, it's really important to make methods, firstly methods that are efficient with energy, because today's deep learning systems are generally not efficient. They use huge amounts of energy to train. I don't have numbers in my head right now, but it's mind-boggling. So just for energy consumption reasons. Also, it's really important with interpretability. So it's really important with models that which we are able to inspect in different ways. There is a lot of research in deep learning on how to make models more interpretable. And I think this is a really important line of work for a number of reasons: fairness, gender equality, other types of equality, but also to ensure that, we can inspect methods to prevent misuse of methods and so on. So so I think it's so I think it's important to strive towards these UN goals, the global goals. So today I will talk about two lines of work in my group that investigates how to get more knowledge out of data and to train models with less data in different ways, inspired in different ways by humans. And I see there's something in the chat. So this reminds me that please interrupt me if you would like to ask a question during the talk. That is completely fine. So please interrupt me, and I won't see the chat easily. So please unmute yourself and ask questions.
I can read the question to you if you like.
Yeah.
So are you thinking learning more like humans in the sense of the actual learning and meta-learning algorithms used to train models, or more in the sense of building inductive bias mechanisms into models that humans have built via evolution?
Interesting. I understand it like this. So the question is on what level should we be inspired by humans? So the work in my group is inspired by human learning in a quite high level cognitive meaning. So there are also a lot of research, also here at KTH, on studying how human learning on a neural level works, and building artificial neural networks that are inspired from the functionality of human neural networks or animal neural networks. These are two different things, and I'm more interested in the former thing. So I'm not really, so I think the way a neural network I mean, a deep neural network works is very, very different from the human brain. And this is no problem. And it's actually, I'm sort of agnostic to whether the underlying machinery is implemented in terms of Gaussian process models, for example, or neural networks, but it's rather the sort of cognitive level functionality. But maybe I didn't answer the question properly. Maybe it was more about, so you talked about inductive biases and fairness. So maybe you could follow up with the person that wrote it.
I could do that. I was just curious about, like you said, being inspired by humans, because from what I read is that we're able to have these rich and useful representations in our mind because we're built in with, for instance, biases of detecting thingness or objectness, and we're pretty good at communication from birth. And that helps us.
Interesting. Yes. Absolutely. Yes, I'm going to come to that. For example, modeling cause and effect. Yes, that is exactly the kind of cognitive aspects of human mind that I think I'm interested in. So now I have removed slides from this in the interest of time that were about compositionality. So, so Lake and Tenenbaum, that talked about this toddler learning about elephants, they are really promoting, it's called programming, probabilistic programming. So it's very much about learning a compositional model. For example, if you're learning about vehicles, to recognize vehicles, you learn about the parts of the vehicle, the functional parts of the vehicle. So if you see a new vehicle with one wheel, you could infer sort of that, oh, this is a wheel, so it must be kind of a wheeled vehicle, but it doesn't look like the others I've seen. But and I think this goes together a lot with objectness. For example, understanding what, if you see a scene, if a human sees a new scene, the human can quickly recognize sort of objects or structures that hang together spatially, and the human can reason about sort of affordances in the scene or functionality, what objects are on top of each other, what objects are connected, and so on. And I think these are very important parts of human-like visual cognition that computer should imitate. And this will also save a lot of training data, because if you learn these compositional models, then you can, it is much more data efficient to learn about wheels, and then you can combine that with knowledge about I know, roofs of vehicles, and then you, instead of learning a sort of atomic model for each vehicle. Yes, this gives me ideas for how I should change this talk. If I'm going to give it again, I should, before I start talking about these two works, I should start first with compositionality. Thank you. So today I would talk about two lines of work. So the first one is, so humans are really good at reason about the causes and effect of what they see. They do not only look at sort of visual correlations or spatial arrangements in a scene. And secondly, humans they very efficiently make sense of sort of chains of events or dynamics over time, and are able to generalize from earlier experience in different contexts. And one reason for this might be because our internal model of dynamics use a lot of recurrence loops. So there are a lot of sort of feedback loops in the brain, not so many linear and serial connections. So I will also talk about little of work by Sofia, who was visiting you 6 weeks ago. So it will be a bit of a recap on how different computer models model information from video. All right, so let me move to the first strand of the research. So humans are very good at looking at making inferences or assumptions about the mechanisms behind what they see and use that. Sorry?
I have a question regarding this latent representation. Like you said that you showed elephant pictures and they're different point of angles and everything. And you said that the human learning is basically involved in lots of inference as well, and it can learn from sparse representation. It may be due to reason that there are many latent representations for a single object that human made in his mind. Because in machine learning, we just take one single latent representation and try to learn that. Whereas human have lots of latent representation, and also human have some mean of combining those latent representation into one single composition that you are mentioning. So is there any mechanism that we can combine different source of or format of data, these latent representations, so that they can form a knowledge, they can form some kind of a thing, so at a cognitive level?
There is a lot of things going on, and we also have a lot of reasoning going on. Firstly, we make use of multiple modalities. We reason about what we see and we connect it to earlier experiences and so on. This goes a bit beyond this talk, but of course this latent representation is extremely complex. It's not only a Euclidean space where you're projecting things. Okay. Absolutely. All right, but so anyway, so the only thing I wanted to say with this slide is that humans very actively sort of, when we observe a scene of something happening, we very actively try to infer why things are happening, the mechanisms behind what causes different things and so on. And then you might ask, I mean, you are all computer scientists, so you have thought a lot about and heard a lot of, you have taken statistics courses where you learned about causality and correlation. So let's take an example to understand why causality is important and different from ordinary correlation inference. So imagine that we have statistics on the number of IKEA stores in different countries, and we also have statistics about the number of Nobel laureates per 10 million people. And then some countries stick out a lot, Sweden up here, and Switzerland and Norway. But overall, it seems to be a linear, very strong correlation, which is kind of weird. But this is, there is some correlation. So you could fit a line to it, and this would have some predictive powers. You could do regression, sort of. You could get statistics on what is the correlation factor between these two measures. But then imagine another task that you would like to change something. So for example, for the Netherlands, say that the government of Netherlands really would like to increase the number of Nobel laureates at their universities. So so then they could get hold of these statistics and say, oh, interesting, there is a correlation here. So it seems like the countries that have many IKEA stores, they have a lot of Nobel laureates. So then we could try to increase the number of Nobel laureates by increasing the number of IKEA stores and see what happens. And then my question to you is why this will not work, obviously. So why won't it work? Just speak up. See the hands.
There's a comment in the chat, and there's no causal relationship.
Exactly. So there is a causal relationship, but it involves some other. There is not a direct causal relationship between these two parameters. So basically, what I think is the reason is that there is an underlying confounder. There is an underlying variable which is hidden, which is the cause of both these factors. And probably it is that, I mean, Nobel was Swedish and IKEA was Swedish. So it's likely that there was a higher rate of Swedes, especially in the beginning of the Nobel laureate. The first Nobel prizes were given more to Swedes just because of this bias. And IKEA stores are, of course, more prevalent in Sweden. So basically, it's something else. So it's kind of hard. So my takeaway from this is that it's kind of hard to see causality from statistics. So, but humans are really good at this. So causal reasoning is a key component, I claim it's a key component in human cognition. So we understand really well about causal effect relationships behind what we see. So for example, when we see this, we see a lot of images of cows, and they usually look like this. So they are out on the grass, and it's usually daytime in the photos we see of cows. So basically cows are out, they are probably not out very much in the night, or maybe you don't take photos of cows in the night, and they like to be on grass. So you don't see cows on a beach very much because cows are kept on grass. So it enables explanations like asking why, and counterfactual reasoning, asking what if. So you could, so using a causal model, you could imagine a cow in the nighttime. What would a cow look like in the nighttime, even if you have never seen a cow in the nighttime, or if there was no training data of cows in the nighttime, but you could imagine that, and you can imagine a cow on concrete ground. And this is a really key ingredient if you want to build a and this would make an automatic model more efficient with data if it also has this capability, because then this model would not, I mean, a model without any causal reasoning ability, given an image of a cow in the nighttime, it would say, I don't know what this is. This is completely unseen. But an automatic method that can reason and think in terms of causality could say that, oh yeah, but this must be a cow in the nighttime because of the lighting conditions. I have seen other things at nighttime and so on. So it could understand the causal mechanisms. And of course, a more obvious reason why it's good for the system is that it could extract more information about the world. It could understand more what is happening in the scene if it has a causal ability. But how can this be done in a computer system? This is the question. So the traditional approach invented in the 40s is randomized trial. Then you need to do interventions. For example, if you want to find out if lung cancer is caused by smoking, you study, you have control groups. So you study smokers and you study non-smokers, and then you see to what degree they develop lung cancer. And then you follow them longitudinally and see how their health is. And then you can understand about the causes and effects related to lung cancer. And this is time consuming, and it can also be ethically problematic. For example, when you do, this is the way you do medical studies. You evaluate a new drug, for example, but it could be ethically problematic to not give the best drug to everyone. So it's a really advantage if you could just take a lot of data that was collected sort of passively without these systematic interventions and controlled interventions. And this is called causal discovery. It's the science about or methods for understanding about cause-effect relationships that have generated the data that we see. All right. So this is work on my PhD student, Rubo. So the classical way of doing causal discovery, introduced around the turn of the century, 20 years ago, is called constraint-based methods. So in principle, they work like this. So we get a lot of statistics about 4 different variables, for example. And then so our goal is to find a directed acyclic graph that describes the causes and effects, the relationships between these variables. So the first thing we do is that we connect all variables with a fully connected graph, and we don't know the direction of the arrows anymore. And then using, for example, the PC algorithm, which is a classical method, we make certain assumptions. We might know that this variable is a source in the graph. There is nothing that causes this variable. And then we can start reasoning in systematic ways and find some of the errors. We might not find all, but we might find some, and this is already good. And there are also score-based methods that work sort of in the same way. But if we only have 2 variables, it's kind of a more difficult case because we don't have any other variables that constrain this. So it's really hard to know the cause and effect. But we can actually make assumptions that enable us to see the most likely direction. And this is based on distributions of the two variables. So we can assume that the noise is additive. So basically that so that, for example, the cause, the effect is an effect of the cause plus some noise. So like this, there is a function of y is a function of x and of some noise term, and this noise term is independent of x. That allows us to we can check whether this assumption fits better. Basically, if the arrow should go this or that way. And in this way, we can do it. But we can only do it in certain cases. We can do it, for example, with linear dependencies. So it depends a bit. It doesn't work for all kinds of functions. So linear dependencies are sort of more regularized and stable and identifiable. So with identifiable, I mean that there is only one possible solution for this this function. There is only one function that could explain the dependency between these two variables. But so there are some cases. Oh, something is happening here. Yes. So okay. So it works in some cases, but it's really, there is a lot more to explore. So we don't really know what do model assumptions mean in different applications. What does it mean that it's an additive noise model? And how can we relax the assumptions and so on? So we have, now I see that I'm running a bit out of time, so I will speed up a bit. So Rubu has he has designed an approach that uses, you could say, a physics-based method. So you could assume that, so for example, if we have the dependency between sunrise time and wake-up time for a person, then this person has recorded it's his or her wake-up time and the sunrise time. And then there is a clear correlation between the sunrise and wake-up time, but we don't know which is causing which. So then we can, so here is a plot of the wake-up time as a function, no, sorry, the sunrise time as a function. Let's see. Yes, exactly. The sunrise time as a function of the wake-up time. This is, of course, wrong. It looks like this. And this is the wake-up time as a function of the sunrise time. Okay. Then you can think of this as the end result of some process where we have moved all these measurements from random distribution. And so you can imagine it's like a flow field, how they have moved from random noise to this distribution. And this flow field, since it's additive noise, we would like the flow field to be the same regardless of, you say the noise should be independent of the cause. So you would like the divergence of this field to be zero. Basically, the way this field is distributed should not depend on the cause, the sunrise time. So then we can look at this field, and it's the same. The points do not change, they have the same kind of motion irrespectively of what the sunrise time is. So this has a very high likelihood of, this is sort of the most plausible. But if we look at the wrong solution here, then in order to move from random noise to this position, you have to squeeze together all the points. And in order to, so over here, you don't have to move the points at all. But here you have to squeeze the points together in the other direction. So this is a very physically unplausible flow field. It would correspond to compressible flow, where you basically have to compress more and more. So for a low wake-up time, you have to compress it a lot, and for higher wake-up time. So using this method, you could deduce that this is the correct causal direction. Okay, so now I will move to the second work, where we looked at dynamical models. So the how I connect this to the theme of human-like modeling is that humans are really, really good at processing temporal information, inferring things and predicting things from temporal information in a very robust and data efficient way. And we are really, since we're really interested in making computer algorithms that are robust and efficient, we want to look at how humans do it. And it turns out, in other words, that humans use a lot of recurrence in their models. So in the human temporal processing models, there is a lot of recurrence. So, and this is in occurrence with, so basically what this says is that humans treat time in a very different way than space. So time physically moves only forward. We cannot travel in time back and forth, only in the movies. And while we can travel in space back and forth as we like. But many of the modeling, the video modeling algorithms we have do not make a difference between time and space. For example, 3D CNNs. Here we treat time as a third dimension. Also in attention models is the same way, that there is no natural direction of time, whereas recurrent models like LSTMs have time. So this is a bit hard to explain connection to this human likeness, but I think it's worth mentioning. Okay, so Sophia did a study on how well these different video models generalize to different data. So this is a key component of human cognition, that we are extremely good at generalizing. So this toddler could generalize from a pen drawing of an elephant to a real image of an elephant. And this is really tightly connected to data efficiency. So this is really, really important for any sort of, what should you say, any algorithm that is useful in the wild should be able to generalize. So it's really important. So we wanted to study whether the choice of model affects generalization ability. And if there is a difference, then we really should go for the most generalizable models. So we also looked in connection to generalization. Geiros et al. Have shown that CNNs, which are the most one of the most successful deep learning models, really important class of deep learning models, they have the problem that they are very biased towards texture. So they recognize objects in terms of their texture rather than extracting these kind of gestalt type of information, like the shape of things or the functionality of things, as humans use a lot for reasoning. So they are sort of very short-sighted. They look at details a lot rather than looking at holistic things. And this is not a problem if you're dealing with very well-defined tasks and very sort of narrow tasks, such as the recognizing a predefined set of classes. But it is problematic if you would like to have a system that can sort of learn continuously and reason about novel things in the world and draw conclusions from very different sources and combine information. Then it would be really important to be able to generalize and to be able to extract sort of holistic things. So what Sophia, so how many of you attended Sophia's talk? Just no one attended Sophia's talk, maybe someone. But then maybe that's good. Then I can give a short. So basically what Sophia did is that she designed 2 data sets that would measure the ability to, firstly, it would measure this kind of shape versus texture bias. Our models, which models are more prone to sort of get stuck on modeling texture rather than looking at shape. She introduced a novel definition of what shape is. So she looked at temporal shapes. So she designed this data set where it's like randomly chosen objects move in temporal patterns. So the classes are in terms of the patterns. So this is a circle class. So all these examples are from the same class. And it's not possible to look at one single frame and say what the class is. You have to look at the entire sequence. And there are 5 classes. And there's 4 visual domains, sort of. And what she did very shortly, I will point you to this paper if you're interested in the details. It has just been accepted to WOCV, and it's accessible from my homepage. What she found was that that if you train and test on the same visual domain, then like here, then 3D CNNs are really good. And Convel STMs are not really, that's the recurrent model. It's not doing as well. But if you go to another visual domain, then Convel STM is better at generalizing. And also transformers are really good at generalizing. Then she has another data set, which is where it's an addition to the Diving 48 data set, which is a very well studied data set of action recognition, where she added she took away all texture information like this and only kept the shape. And she also took away all the shape information and only looked at the texture. And then she studied how well these 3 different models could classify the motion. So it would be really good with a model that could perform as well on this only shape information version of the data, because that means that the model has totally extracted the important information from the data. And I'm not gonna, in the interest of time, I'm not gonna go into detail. So what is happening now? Why can't I move on? Yeah, so she confirmed that in very short, that the Convel STM generalizes better. Yes, but what I think, what I would like to bring forward, even though I'm over time, bring forward from this is that it's also really important that the model has understood the structure of what it's looking at. So that is a connection to the causality work of Ribot, that you really understand sort of the inner structure of the system that you are studying. So what the system is studying here is that it's looking at people doing this diving, this figurative diving figures, actions. So there are 4 attributes. You can have different kinds of takeoffs. You can have different number of somersaults, twists, and you could also do different things in the air. You could tuck together in the air or keep straight. And if you look at what the different models, if they have selected the right if you look at what how many correct attributes they have gotten right, so they make a lot of misclassifications on the classes, because the classes look very, very similar. But you could also study, okay, if they make a misclassification, is it to a class that contains much of the same attributes? So it could be, oh no, it got the number of somersaults wrong, but otherwise it was a correct classification. So if you count the number of attributes it got right, then you can see that the Convel STM is much better at counting the number of attributes. So that indicates that the Convel STM is quite good at modeling the true mechanisms behind what we see. Yes, and there is a lot more detail in this paper, of course. So there are indications that this recurrence is good for robustness when you change to another domain, if you go from pen drawings to a real image. And this is connected to texture bias, probably. But foremost, that it's really important to think about the fundamental low-level choices of methods. Yeah, to summarize, humans learn from few examples in a modular way, and we reason about our observations, and computers should too. And I described 2 approaches for that connected to this. And thanks to my group and to my collaborators. And you can access my homepage through this QR code if you like. Thank you so much.
Thank you, Hedvig. Do we have some questions? I think we have time for some short questions.
I have a couple of questions, but I can take the one or two.
Yeah.
Okay, first of all, thank you for a very valuable and informative lecture. So one question, do you envision, so just to summarize, you talked about models that could deal with causality, with composition, like parts whole, and you've also talked about temporal aspects of models. Do you envision that there should be some type of sequence of doing these in some ultimate model that can do all three? Because I'm thinking, like, before you can talk about causality, you have to talk about hypotheses and entities, and before you can talk about entities, you have to somehow talk about segmentation between what is irrelevant and what is relevant. So is there a sequence of ordering on how we should approach this?
Yeah, good question. I think that, so there is still, causal discovery is still a quite young field, and it's in many ways quite far away from machine learning. It's like probabilistic machine learning and reason about uncertainty. So I think it's really important to start merging causal reasoning and reasoning about uncertainty. So in causal models in general, you have to model everything, and it's like deterministically. So you have to find the correct solutions. The system has to be identifiable. It's very, the terminology is very much in terms of control, automatic control, that you have an identifiable system and you identify the underlying variables. But I think it's important, so maybe you don't have to discover all the cause and effects of all aspects. Maybe you only have to have some notions of cause and effect, and then there is a lot of residual information that it doesn't really matter what this comes from or if it's caused by the same thing and so on. So I think, yeah, so I think that's important to start bringing probabilistic machine learning, deep learning, and causal analysis closer to each other.
Thank you.
I can also ask a question, maybe. Thank you for the interesting talk. I was more wondering about your second paper that you presented about robustness. And you talked about generalizability, and there was an experiment showing the generalizability as well. But how much do you think the experiment is actually fair with regard to the result that you are getting? So, I mean, generalizability with regard to the recurrent things. Of course, we don't expect, for example, CNN perform best or be the most general. I don't know, like, can you comment on this?
Yeah, so I think that was exactly the point. Basically why we evaluate these three models is that so 3D CNNs are they are the state-of-the-art models for video modeling, and they are extremely successful on sort of in-domain tasks. So so Convel STMs or LSTMs, recurrent models in general, have come a bit out of fashion because they are not as successful on in-domain tasks, especially if you have a lot of training data. 3D CNNs require a lot of training data. They have a lot of parameters. But if you have a lot of training data, they are able to fit very well to this training data. So we wanted to sort of make a statement about yes, but if you're interested in generalizability, then it might be actually worth to revisit these recurrent models that are shown in neuroscience to be more in line with what's happening in human temporal cognition. So it's so I think definitely that experiments are fair to 3D CNNs. We give the 3D CNNs exactly the same information that we give the. So for example, what we see here is that, so I think S1, so we can look at S2 and 3T. So S2 is the case where you only see the swimmer, and T is when you only see the background. And then we clearly see, so we have calibrated these, so we have stocked the training when the three models get the same result on the in-domain task, which is classifying the original images. And then when we present, then we have three architectures that are trained in an equal manner and perform equally on the in-domain task. And then we present this new data to them in the same way. So it's very fair. And then we see that the Conv-LSTM is better, generalizes better. But when you show only the background, the Conv-LSTM fails, which is, it tells us something about the texture bias. So it says basically the Conv-LSTM has not learned very much about texture. But this is the important part, result, showing that the Conv-LSTM deals better with only seeing the shape information, which is the part that generalizes more to another. I mean, if you would see the divers out on the ocean instead of indoors, you would not have the same background, but then the Conv-LSTM would do better.
Thank you.
Hi, Hedvig. I see somebody before me. I had a question too.
Yes.
Should I start? Okay. I'm an old student of yours. I'm not sure you remember my name, probably 9 years ago at KTH. I started my master program in machine learning with you as a teacher.
Okay.
Yeah. So I'm still a researcher now in AI for production engineering, but I'm very passionate about this causal inference thing. I did the thesis with Anders Scholz at Rice. I think he was kind of talking about the same causal inference and the importance of it, and to not infer things from statistics because it might be devious. And I really like your time approach. I've thought a little bit about it. And I don't want to go in detail, so that was just a recap of what you said. I think I like it very much. I'm going to show you an image. I can post it in the chat. Is one of those images that you can generate through these latest algorithms that you write a sentence and then they produce an image that is photorealistic. Yes. So if you open this picture, it shows a salmon in the river. So that's the sentence you write, and then the AI has learned the concept of a salmon, a river, and tries to put it together in an image. The problem is that it uses a salmon like the one you've cooked as a meal, And then you see this salmon that looks like the one you should have in a plate, but has the semblance of a fish, and it's effectively in the river. So it's a funny thing. I think this kind of AI was built for artistic reasons, and we can laugh at it. But the question I have is like, yes, we should learn computers, actually, algorithms should learn to infer things like humans do. But how do we use this knowledge in a way that the algorithm, for example, can come back at humans and ask the question, is this like a real salmon to you? Or get experience from the real world? Because we put all this experience into data sets and we try to build better data sets, I guess, but we don't have a way to actually go back in the real world like humans do very easily. We can test ideas, we can build the concept of a cow and we can put it in a beach, and we can ask somebody, have you ever seen a cow on a beach? And then if they say no, we can, you know, adapt our concept and kind of reason. So I don't know. I'm thinking maybe reinforcement learning is the way where I can see an algorithm testing this concept, causal concept, in an easier way. But what do you think about it?
I think that, maybe reinforcement learning, but more self-supervised learning. I mean, all these methods, I mean, stable diffusion, so they're built on stable, about self-supervising ideas where the method discovers things autonomously from data. So reinforcement learning is kind of limited because you need a feedback signal, but you can get this feedback signal from the data itself using self-supervised learning.
I say reinforcement learning because there I see a different paradigm. For example, you generate the rules, but the environment is created automatically from those rules. So it's a little bit more strict in the sense that you can't be creative, but the computer can generate their answers in a certain way and then get the feedback automatically on those. In fact, they beat it, for example, the best Go players with rules that didn't exist for the players. They found strategies that were completely novel. They couldn't have asked the player, is this the best strategy?
So we're running so much over time, but I just want to say that was a very, very controlled domain where you had a very clear feedback signal, which was.
So my question is like, what is the way forward for a sort of a trade-off domain? Where would you look into?
Self-supervised learning.
Okay, thank you.
Yeah, that's my bet.
Thank you very much for your presentation. I'll be very quick. I was trying to fully understand the underlying assumption when you were deriving these arrows, direct arrows on your first, on the first work of Reibu.
The one we see here.
So you had the previous slide, I guess, where you were getting the acyclic graph.
Yes. There. Yes, sorry, I don't have time to present the PC. It's called the PC algorithm. After the inventors of PC algorithm. So you should look it up. It's an algorithm for inferring the direction of some arrows. Okay. It's a classical, it's like the first classical causal discovery algorithm. It's from 2002, maybe, or 3, or something.
Okay. I will look it up. Okay.
Yeah.
All right. So then it's time to round up, and thank you, Hedvig, for this interesting talk, and thank you
so much
for all the questions. So next week we have a presentation by another professor from KTH, your colleague Ricardo Vinuesa.
Oh.
About modeling and controlling turbulent flows through deep learning. So welcome back next week.
Thank you so much for having me. Bye-bye.
Thank you for coming. Bye-bye.